All right. Welcome, everybody. First of all, I would like to thank organizers Elke and Arne for organizing this exciting summer school. It's pleasure to be here. My name is Fedor Jelezko. I'm representing University of Ulm. It's on south of Germany, but also a Center for Integrated Quantum Science and Technology. It's a joint quantum center between universities of Ulm, Stuttgart, and Karlsruhe in Baden-Württemberg. And it's really great to hear about development here in Rheinland-Pfalz and the center QUIP, which is supporting this summer school. I will start my lecture with introducing the quantum sensing as a field. And in the quantum sensing, just a second, we typically work with small-scale quantum registers. And if we compare the field of quantum sensing with quantum computing, there are a lot of similarities. And the question whether you can use your quantum system or your control tools for quantum computing or quantum sensing depends whether your system fulfills some requirements. And for quantum computing, there are very known set of requirements to be able to build a useful quantum computer formulated by David DiVincenzo. I shortly highlight them. You need a scalable physical system. It's one of the first requirements. You need to be able to scale up your register to a very large number of qubits. You need to be able to initialize and measure your system. You need to have long coherence time, and you need a set of quantum gates, including a single and 2-qubit gates. And although many quantum systems are on the market for quantum computer, it's sometimes very difficult to fulfill all these requirements, especially scalability. To scale up the system to millions of qubits is sometimes challenging. For quantum sensing, requirements are quite similar. You need a system that have resolvable energy levels. They need to react on external parameter. You need to be able to read out, initialize your spin, and coherent control is also necessary, but not always having universal set of quantum gates. Sometimes even coherence without entanglement is useful for quantum sensors. And in case of entanglement for quantum sensors, already very small system, 1, 2, 3 qubits can provide the quantum advantage regime. And so I think that the field of quantum sensing might deliver the very first useful kind of quantum computers. There is no border between this field, but control of a quantum system under control I'm going to discuss is a nitrogen vacancy color center, nitrogen replacing carbon in a diamond lattice and a vacancy nearby. This is color center because it absorbs and emits the light, and when present in part per million concentration, it's already give a pink color to natural and synthetic diamonds. NV center possesses very interesting spin and optical properties, in addition to strong absorption and emission of light between a ground and excited state. The ground state nature of this defect is a spin triplet. So it possesses a magnetic moment in the ground state, and energy levels of this spin triplet state can be initialized and read out optically. If you excite your color center from the ground state to excited state, for 2 out of 3 spin sublevels with magnetic quantum number plus and minus 1, there is a strong Schelvin to a metastable singlet state, and from this state the system decays in the third sublevel with magnetic quantum number 0. And this turnover ending always in one state lead to strong polarization of the system. In addition, this MS equals 0 state provides long cycling, and if you start to excite from this state, the system emits many photons, up to about 20 to 30 million photons per second, which can be detected, and that's also allow you to detect this color center optically, even on a single site. Fluorescence intensity, the number of emitted photons per second, also provide you the access to measure the spin state in a very sensitive manner. Here I show you how it works. So if you measure the fluorescence intensity and you shine a laser at one time point, your response of the systems, the number of emitted photons will differ between situations with your system to be in +-1 state or 0 state. Owing to this passage to a singlet, +-1 state go to a dark state, a singlet, and then you get less photons emitted compared to situation where you start your excitation in magnetic state, in a spin state with magnetic quantum number 0. That provides you higher fluorescence intensity. By measuring this difference, you can measure the spin state. Typically, we don't collect photons very efficiently, and we lose a lot of them in our setup. So the experiment based on fluorescence detection typically is not single shot measurements of a spin. You need to repeat this many times, but I will also give you example where you can do very efficient measurements of the spin state of this color center in a way that you can every time when you measure, every time get results regarding the spin state of NV center. Also, if you have questions, so you are very welcome to interrupt me. Just raise your hand and I will be happy to take a question. For applications in quantum sensing, it's very essential that we can create color centers on demand with very high precision. In fact, many color centers have been discovered in diamond after first experiment with NV centers, but not all of them are yet at the stage where you can create them with nanometer accuracy. But for NV center, you can do this. If you take very pure diamond lattice and implant single nitrogen ions, either using focused ion beam or using nano apertures like holes in atomic force microscope tip or E-beam lithography created patterns, so you can create arrays of NV centers, and positioning accuracy of this technology is about 10 nanometers. In fact, in Z direction, the distance from the surface of diamond to the NV center, the accuracy is even better than this, can reach a few nanometers. So you can place your color center with very high precision, and from my perspective, actually ability to implant NV center and also ability to create a diamond which is free of unwanted NV center is one of the major developments in the field, which actually made possible all the applications of color center. Material science is very essential for the success of this NV center based research. The experiments with single sites, single NV centers, is typically a combination of the confocal microscope, fluorescence microscope, with some addition allowing microwave control of NV center. We excite color centers using 532 nanometer laser, focused laser beam to diffraction limited spots. We collect fluorescence emission. If you remember from the last lecture by Erbacher, there is a stock shift, and fluorescence emission has a different color, is red. So you collect the red fluorescence emission separated from the excitation laser by filters, and then measure number of emitted photons using avalanche photodiodes. Often, in order to make sure that we have really a single NV center, we can measure the G2 function of emitted light, fluorescence autocorrelation function, show an photon anti-bunching dip. The photons are separated always in time, and this separation in time give you a hint that emitter is really a single atom, because many atoms can emit photons independently, but for a single atom, you always get a delay between detection of the photon and then the excitation leading to emission of the next photon, and that leads to appearance of this dip in the relation. We add, in addition, microwave line, allowing to excite spin transitions. And if we apply both laser excitation and microwave excitation, and our microwaves are hitting the transition frequency between bright and dark state of NV center, that leads to redistribution of population, and we have a drop in fluorescence intensity in this double resonance optical excitation and microwave excitation by about 30%. So that's not 100%, so that has some implication in sensitivity, but quite high optical contrast for different spin state. And this measurements and fluorescence intensity now give access to measure the dynamics of the spin state associated with the ground state, ground triplet state of NV center. This is how the heart of experiment typically looked like, how the diamond piece looks like. We have a synthetic diamond with a microwave line. I don't show here microscope objective, it comes from the top. Here you see that the microwave line gets very narrow here, and NV centers are implanted here between the signal and the ground line. And with this, we can also do a coherent drive, coherent control. We can drive our spins by applying microwave pulses and by measuring fluorescence intensity. It's always fluorescence measurement, always optical measurement. So we measure fluorescence intensity as a function of the duration of the pulse, and we can see, for example, Rabi oscillation, where we drive the system from one eigenstate to another. But if we stop the pulse here, we can leave the spin system in a coherent state. And that is a very important resource in all quantum sensing scenarios. So ability to generate coherence, ability to excite coherent states, which are now sensitive to external perturbation, is at heart of any quantum sensing scenario. Right, I mentioned it before that typically experiments are performed many times, because in 99% of cases where we try to measure the NV center, we are missing the photon, and the measurements is not giving any result. So it's not a single shot measurement. But in some cases, this single shot measurement is possible even under ambient condition, and I give you a few details how we can do it. For single shot measurements, and single shot means that if you have a system, have a spin, and you try to measure every time you get a result, every time you get an answer in which state the spin is. In order to reach this regime, we use not only electron spin of NV center, but also the nuclear spin associated with nitrogen 14 or nitrogen 15 stables isotopes of nitrogen, which are always present in NV center. If you look in the magnetic resonance line, if you zoom in on NV center transition, you start to see fine structure, your hyperfine structure. These three lines correspond to three states of nitrogen 14 nuclear spin. And this nuclear spin is very robust. Even when you excite your color center with laser pulse, it goes to excited state, it relaxes. You typically don't flip your nuclear spin. It still carry the information about the state. And so if you now use this two-level or two-qubit system with one qubit and V-center electron spin, which can be measured optically, and the second kind of a memory spin, nitrogen-14, which keeps the information about the spin state. You can improve the fidelity of your measurements or efficiency of the measurements. How it works, so you repeat your measurement many times. If I want to measure now nitrogen-14 nuclear spin, I do a selective bypass on the transition corresponding to one of the hyperfine component of the spectrum. So I apply a bypass here. I apply a pulse which is selective to one sublevel or one of the component of this spectrum. And with this bypass, I flip the electron spin of NV center only in case if nuclear spin is in -1 sublevel. So then I measure my electron spin. It gives me optical contrast. I might lose the photon, but then I can repeat the measurement again. And by repeating this many, many times, I get a signal which is amplified. I can measure now the nuclear spin state many, many times without losing it. And that's allow me basically to do many copies of this state and measure sort of even in case if I lose many of my photons. So making many copies here and doing some redundancy in this measurement allow me to improve the sensitivity of spin detection. So for this, I need two qubits. One is a robust qubit, a nuclear spin, and the second is a qubit which I can measure optically, the NV center electron spin, and I also need a gate, exactly what is also necessary for quantum computer, a gate which is flipping the electron spin conditionally on the state of the nuclear spin. So now I show you how it works. So this is now the protocol where you continuously run this bypass and then measure the fluorescence intensity. I plot here fluorescence intensity versus time, and it's a real-time picture of the light emitted by a single NV center, which now have very clear jumps between a low fluorescence intensity and high fluorescence intensity. And so you see there are dark intervals with a duration of about a second, and bright intervals. And so these dark intervals correspond to situation where you hit your nuclear spin state with your pi pulse, and this situation persists for a few seconds. And in case if you are not in a right nuclear spin state, your microwave pi pulse don't do anything, and you are in a bright state. And what you see is a quantum jump of a single nuclear spin between nuclear spin up and nuclear spin down. And observation of these quantum jumps, so-called quantum non-demolition measurements, is a signature that you can measure your spin very, very efficiently. Yes, please.
Thanks. I have a question about how this measurement works. Can you, like on the last slide, you showed us the same graph on the top right, and then you say, okay, we go, after we're done with the measurement, we go back and repeat the thing. And nothing happens in between, right? In between those repetitions, nothing happens.
Time trace, there was nothing happening always, but it's continuous. So a pi pulse, a microwave pulse, and then a laser pulse, and then again microwave pulse, a laser pulse, and so on. So it's a continuously microwave pulse applied to the system plus a laser pulse. Actually, the similar trace can be recorded if you just shine a continuous microwave and continuous laser. So then imagine that your nuclear spin state is in this -1 sublevel. Then your microwave will pump population here in another electron spin state, and it will be darker. And it will stay dark as long as nuclear spin state is preserved. It is, of course, not infinite. There are some perturbation coming from an environment which lead to this jump to another state. But in principle, this kind of time trace can be detected just by shining the microwave and shining the laser at the same time.
Okay, I want to say I'm a theorist, and I don't really understand this noise too well. When I look at this circuit picture, I'm thinking the first time you measure the electron spin, you should collapse the nuclear spin onto something.
First spin would be in a superposition state. By this measurement, it will collapse on 0 and 1 or 1. But the next measurement will, because this now is at a classical state, and the next measurement will not collapse anything. It will already start with a classical state, and it will measure it again and again and again. So the non-demolition in quantum non-demolition measurements is basically about non-demolition for eigenstate. So even the very beginning here, the system was in superposition of 0 and 1. After measurement, it will collapse to 0 or 1, but the next measurements will continue to measure 0, 0, 0, 0, 0, and so on. So after very first collapse, the system will then remain in eigenstate, which you will continue to measure here for some duration before the system gets flipped by some environmental perturbation. Yeah.
And why do you keep measuring? I mean, if it's just, what are you trying to find out here?
I would like to now discriminate. I would like to discriminate between nuclear spin up and spin down. And so if I have this trace and I measure the probability of photo counts, I get the two-peak distribution. Part of events where I was in a dark state with less number of photons correspond to this plateau, and part of events where I had a high fluorescence corresponding to this peak. And now if you put a threshold, which would be a line here, I can now define for my measurements. If I have a fluorescence lower than the threshold, I know that I'm in a spin down state. If it's higher than threshold, I am in the spin up state. It's kind of digital measurements of the spin.
So is this graph on the right here the calibration for the measurement you really want to do?
Kind of calibration of measurement, but it's also interesting measurement itself, because it gives you the dynamic of this nuclear spin. So the duration of this interval give you a relaxation time of nuclear spin, but it is indeed some kind of, it can be used for a calibration for the single shot measurement.
I have a question about what's the meaning of the time here. And you mean you turn on the microwave? Is it a pi pulse, or just the time is the time of microwave when it is on, and you use a pulse laser to read it out?
Details are so that microwave need to be long enough that you only hit one transition and not the other one. So the microwave pulse need to be weak enough that the pi pulse duration, let's say, is longer than a microsecond. Then you will be selective. And the laser is then should be long enough to polarize nuclear spin. So you need to reset nuclear spin before applying the next pi pulse. Typically, it is about a microsecond duration of a laser and a microsecond duration of the microwave. And so the whole readout takes you 2 microseconds, but then usually you lose 99% of photons. So even though you measure every microsecond, but in 99% you don't get any results. And by repeating about 1,000 times, so let's say it's now 1 millisecond, now you get enough photons to discriminate between this spin state. So typically one need about 1,000 measurements to get enough separation between bright and dark state, actually. All right, so we have now a quantum non-demolition measurement, so allowing you to measure the nuclear spin state with very high fidelity. And this is measurements of nuclear spin state, not electron spin state. Nuclear spin state is not very good sensor qubit, but you can swap the information. I will show you some examples later between electron spins and nuclear spins. So you can use these measurements often also for measuring the state of the electron spin. All right, so this is about techniques that we use for measuring our qubit. Remember, for criteria describing the properties of quantum systems that can be useful for sensing, we need to initialize, we need to read out the state, and this initialization and readout can be done very efficiently using optical techniques, fluorescence emission, even all the way to a single shot. And during these two lectures, I would like to show you some applications of in-V centers endowment for quantum sensing, especially in nanoscale nuclear magnetic resonance, but I will also touch a little bit sensing of radicals and cells and temperature sensing, and if I will have time, I will also highlight some development in the field of enhancement of magnetic resonance imaging using optically polarized spins. So this is kind of a plan for today, but before doing this, I would like to discuss the sensitivity and dynamic range as well as spectral resolution of these diamond sensors. So we have learned now how you can measure the spin state, but how sensitive is your in-V center electron spin if you want to measure different external parameters, to which parameters in-V center is sensitive. So for sensing, we need that the qubit is responding to external perturbation you would like to measure. So it's very different for quantum computer. Quantum computer, you want to isolate your system as much as possible from the environment, but for quantum sensor, you need some responsivity, and here there is a difference. So very well protected system might be not very good sensor. So for sensor, you need to protect it against all the perturbation except your signal. The system needs to be open to a signal. So how to use qubit as sensors, especially at nanoscale? Typically, you take your in-V center, you bring it very close to the object you would like to study, for example, electron spins on nuclear spins outside of diamond. And if you get close enough, then your in-V center can act as a compass needle and measure the magnetic field of external spin. How to convert a measurement that we have discussed before, measurement of spin state, to a magnetometer. So it can be very intuitive. So if you can measure the frequency of the transitions of in-V center between a bright state, ms equals 0, and dark state, -1. And if you apply a magnetic field, then the transitions are getting affected by external magnetic field. And if you know the magnetic moment of your in-V center or ferromagnetic ratio, and you measure the energy separation, then you can reconstruct your magnetic field. And this is the basic of magnetometry. You measure the transitions of the spin state of in-V center. You use this knowledge on energy separation of spin state to reconstruct the B field amplitude. In some cases, you can also do vector measurements. In any sensing scenario, there are several benchmarks. One is precision, that's sensitivity. Another is dynamic range. I can be very sensitive, but only measure in some very small range of fields. So the dynamic range shows you how broadband you can be. And the frequency resolution, often you measure not the static fields, but AC fields. An ability to resolve two different frequencies in the spectrum is very essential. So sensitivity, dynamic range, frequency resolution. Those are important parameters for any sensors, including NV centers, spins associated with NV centers. And we will discuss very briefly these parameters as benchmark. And there are similarities actually to clocks that you have heard during lectures by Piet Schmidt. Also in clocks, the ability to track the phase of oscillator and lock the phase is very essential. And it turns out that the precision of clocks can be linked to very similar parameter of quantum system as the sensitivity of the sensor. So the best way to measure the separation between energy levels is not just to track the spectral lines, but to excite coherent superposition state, spin down plus spin up, leave it to precess, and you can visualize it in a block sphere. You flip your spin to equatorial plane, it starts to precess with a Lambda frequency, and then after some time you pick up this phase by again flipping the spin either up or down, depending on the position of the spin in an equatorial plane in this block sphere representation. The phase acquired by the spin is proportional to the magnetic field with some prefactor associated with here magnetic ratio. And the phase is also proportional to time. The longer you can precess, the more phase you accumulate. And you can then convert this to a minimum measurement field. If your noise is only spin projection noise, this noise associated with this quantum jumps, when you measure the spin, there is a collapse of the spin state. If this is the only noise you have, then the smallest measurable field that you can measure is given by the equivalent noise. And this is, again, atomic parameters, 1 over G factor, and then 1 over square root of number of atoms you have, measurement time tau, and the total measurement time you have in your experiment T. So the longer is coherence time, the longer you can leave the system to precess, the better it's your sensitivity. And this is very intuitive because the more turn your block vector do, the smaller alarm frequency it can pick up to give a measurable phase here. So the strategy to improve the sensitivity for quantum sensors usually rely on basically an avenue to improve the coherence time. So the longer is the coherence time, the longer you can leave the spin to precess, the better will be your sensitivity. For ensemble of NV centers, you can also enhance the system by basically multiplying the signals or adding the signals of many NVs, having this N to be large, usually allow you to improve the sensitivity. But for nanoscale sensing, often you are obliged to work with just single NV centers, and then N is just 1, and there is nothing else to improve except the coherence time. So it's very important to have a long coherence time to reach high sensitivity. So for NV center, yes, please.
Just to see if I understand correctly. So tau is limited by T2, basically. And T studies more or less a statistical thing, how many times you repeat in the overall. Okay. And what is the typical order of magnitude of delta B? And how far are we from that?
The phase is proportional to tau, the time you precess, and that's linear, right? But then because you repeat measurement many times, so if you have very long coherence time, you win linearly with your time, but then you have less measurement because every measurement takes longer, and that's why you get 1 over kind of square root here. So because you win a number of measurements. Typical coherence time for NV center, it's at room temperature, it's about 300 microseconds in a best case. So a single measurement can take you up to 300 microseconds, and then that would translate, if you put here the numbers, like the G mu B will be about 3 megahertz per Gauss. That will translate to the sensitivity of about 10 nanotesla per 1 second measurement time. We will have some examples later to see that for a single NV center. About 10 nanotesla single NV center can measure if you measure 1 second. That would correspond to about 10,000 averages. So that's so the application of these NV centers are numerous, and we will discuss a few of them, but I will maybe start with using NV centers to measure other spins. The magnetometer able to measure very few nuclear spins outside of diamond lattice, and this ability to measure nuclear spins with high sensitivity is very essential for developments of nuclear magnetic resonance and magnetic resonance imaging. Typically, in nuclear magnetic resonance spectroscopy, you approach the coil to your sample, and your sample consists of many nuclear spins. You apply pi half pulse to these nuclear spins and measure induction signal. The relatively high noise in these measurements associated with this coil-based detection lead to a relatively low sensitivity. In conventional NMR, you need about 10 to the 12 nuclear spins to be detected, and this is if they're all polarized. Typically, they're not all polarized, but they are kind of distributed in a sense that there is roughly the same population of nuclear spin up and nuclear spin down, and very tiny fraction, about 10 to the minus 5, contribute to the signal. And that's translates to the 10 to the 17 spins that you need to have enough signal-to-noise ratio. About a micromolar of the species, you need to get enough signal to just start to see your nuclear spin. That's why usually nuclear magnetic resonance is not about detecting single molecules. But new detection scheme, new magnetometers can be a game changer here. There is a strong effort in NMR community to replace this coil with very sensitive magnetometer. It can be atomic vapor magnetometer. It can be also atomic force microscope with magnetic tip, or NV center in diamond. So I mentioned before that detection of this nuclear spin is about detecting the AC signal, alarm or precession frequency. The nuclear spins are precessing and creating magnetic field at your sensor, and for this you need to convert your NV center from a DC magnetometer to AC, to a spectrum analyzer. This can be done by applying pi pulses, and you had already in a lecture by Erbacher overview of different dynamical decoupling technique, but here I turn it to a very simple picture. So if you apply many pi pulses, you create a so-called spin echo, and this spin echo, these pi pulses are refocusing static fields. So by flipping the spin forcing back, you can completely cancel the influence of static field acting on this quantum system. And if you apply many pi pulses, it's not only static fields that you can cancel, but you also cancel many perturbation frequencies except one. The one which still influence your color center, the one which frequency exactly matches the repetition of these pi pulses. You can have an analog picture in optical spectroscopy if you have a grating and you send a multicolor light after diffraction. There is a positive interference of one particular frequency in one direction. And this, the maximum diffraction direction, all your waves are interfering positively. The same in time domain happens here with this train of pi pulses. So if your AC field matches, the separation between pulses in time domain, your NV center will still acquire the phase associated with action of this AC field, and you can, by making this train of pi pulses very dense, you can create a narrow filter function which you can tune by changing the time between pulses. In this optical analogy, you would change the angle of grating, and that's really to kind of change the distance between, effective distance between traces. In this case, we change the time between pulses. This is how to build a spectrum analyzer out of NV center. And so the more pulses you can apply and the longest coherence time, the better is your spectral resolution. So coherence time is still playing a role here. Coherence time of sensor, at least in this very simple picture. Here I show you example how you can detect nuclear spins. Now using this spectrum analyzer, we took NV center, which is just about 2 nanometers from the surface. We have created this by ion implantation. Yes, please.
Hi, Fedor. So in the XY8 sequence, so the total duration of the sequence should be limited by the coherence time, right? Okay.
Basically, the width of this filter function, 1 hour coherence time, but also the sensitivity. This sensitivity estimate that I show here is also valid in this case. Yeah.
Have a higher coherence time, then we can apply these pi pulses in between with more number of pi pulses can be applied.
Large number of pi pulses, but you will be limited typically by this few hundred microseconds. And think about the duration of pi pulse is about 10 nanoseconds, right? So how many pulses you can apply? So you can do to a few tens of thousands. And if your pulses are right, then so you can do very high Q factor filter function. Like this width to the absolute frequency will have a 10,000 Q factor. Yeah. All right, so here's example of this spectrum analyzer. And we sent 2 nanometers from the surface of diamond, and we put a drop of oil. Oil do have hydrogen nuclear spins, and you are so close to the surface that actually even a single nuclear spin now produces considerable field. We apply many of these pi pulses, about 10,000 in fact here, and we tuned them to a situation where the tau is more or less matching the Larmor frequency or inverse Larmor frequency of nuclear spins. And now we change the time between pulses, and we sweep the filter function of our AC magnetometer or spectrum analyzer. And this is the result, the signal detected by this NV center. It's always a fluorescence emission in this case. So what we measure is a change of NV center fluorescence. What I always plot here is fluorescence intensity of my NV center, but now as a function of the changing of tau between pulses. And it has a response exactly at the Larmor frequency of nuclear spin. By integrating this surface below this area, you can also estimate what is the power spectrum, what is the amplitude of this magnetic field associated with nuclear spins. So the sensing volume is, in this case, is just about 10 cubic nanometers, but the magnetic field that you get is about 2.7 microtesla. It's not a very, very small field. Although the number of nuclear spins is very small, but because you are so close that even a single nuclear spin creates enough magnetic field to be detected. And this is just a demonstration of detectability of nuclear spin. But the interesting question is, of course, what you can learn from these experiments. And learning the hydrogen Larmor frequency is maybe not a very high information content experiment, but actually detecting nuclear spin in biomolecules or measuring metabolic reactions, this is a very big impact results. I give you some example how you can apply this NMR to biomolecules. This is a joint work with Mikhail Lukin group at Harvard University. we have attached a protein, ubiquitin, to a surface of diamond, again having it center about 2 nanometers from the surface, and we repeated this NMR experiments, and maybe just a few words about attachment. So the surface of diamond have been modified, starting from carboxy group, then going to amino group, and then attaching via cross-linking the protein. What you see on the left is the IFM, atomic force microscope picture of the surface of diamond before attachment of biomolecular protein. On the right side, you see what happens after you link it, the protein, the surface gets rough, and every of these spots is a protein sitting covalently bound on the diamond surface. And now NV center is sitting below one of these proteins. You can think it's not really.
So a question, I'm sorry to interrupt you. So you put things on top of a diamond surface, and you also somehow estimated the volume that you sensed, but how do you estimate sensing radius of the NV?
A very good point. So the volume we define, the sensing volume, is a volume from where about 70% of signal is coming. Because we are measuring the magnetic field from external spins, and this field decays as a third power of the distance. That means that the spins that are located closer contribute more to the signal. And so this estimation of sensing volume to be 10 cubic nanometers, it means that 70% of the B field is coming from this sensing volume. And the spins that are more far away, somewhere here, they still contribute to tiny fraction of this. And the contribution decays as a third power of distance with the distance from the surface. And so here in this picture, it's also, you can see that the packing of these proteins is very dense, but the NV center sits below the surface and only will see one of these proteins, and the other one will not really contribute to the signal. Yes? We use single NV behind it, yeah, exactly. Yeah. Right, and here you see a result of experiment similar to that I have shown before. We changed it now between pulses, but now we converted this to the frequency, and you see spectrum of protein detected by NV center. This protein was a little bit modified to make it more distinguishable from the environment. So it was enriched with deuterium and carbon-13 to make sure that what we detect is not some water around, but really a protein. And so what you see here is the frequency of the deuterium alarm frequency and the signal associated with carbon-13. Very noisy spectra acquired for about 20 minutes to get this signal to noise. But remember, it's now a single molecule and not a micromolar. A micromolar means 10 to the 17, 10 to the 16 molecule. Typically, you need an NMR to detect the molecule, but here with this very small magnetometer, because you are getting so close to the molecule, you can detect a single one, and you can do it even in a very low magnetic field. So it's very interesting. This experiment showed that you can detect a single molecule.
How can you make sure that it's a single molecule in the sensing radius?
It's because we can calibrate, we can calibrate the depth of NV center. Actually, for each of these NV centers that we have been using here, we did this experiment. And because we know the density of hydrogen spins, we can, from the measurements of the amplitude of the field, we can measure the distance with angstrom precision to the surface. So once we know the distance to the surface with very high precision, and we find exactly the same NV center later, when a protein is attached, we can claim that it's really a single molecule. Single molecule in sense of that signal is coming must be from a single molecule. Actually, it turns out that it was even not really like whole molecule was contributing to the signal, but only a part of molecule. The NV center was so close that within the sensing volume, only a part of protein was kind of massively contributing to the signal. Sensing volume was smaller than the protein.
So in your case, dielectric dilution doesn't make sense, and for you it's just a choice of the NV, that is how close it is, and that's how you make sure.
We rely on a knowledge how close NV center is to the surface of the diamond. Yeah. All right, and so detection is possible nowadays. So we can detect this molecule even without labeling now. So far, the only technique that can measure at room temperature single molecules is fluorescence microscopy, but relying on detecting fluorescent labels like GFP or Alexa dye. But here we can detect nuclear spin inside of the protein. So it's a label-free technique. So it's very interesting. But detection itself is not the whole story. What you want to do, you want to measure the structure, you want to measure dynamics of molecule, and this is a big research avenue. Yeah.
Just like to put it into perspective, how long was the data acquisition for the?
About 20 to 30 minutes to get this spectra. Yeah, so it's pretty long. Yeah, it's pretty long. Actually, so improving this, it's one of the challenges. Yeah. But first, maybe a few words about spectral resolution. So this spectral lines, if you look on the x-axis, quite broad. So the line width of a few kilohertz is enough to distinguish between different nuclei. So we could distinguish between carbon-13, deuterium, or hydrogen, and that's give you a chemical composition of the molecule. But really interesting questions are coming when you can answer, or interesting kind of developments are related to answering the question about complex structure of molecule, not about just measuring the chemical composition. For example, if you can measure chemical shift in NMR, you can already distinguish between alpha helix and beta sheet. Measuring J coupling allow you to get access to 3D structure of proteins, and nuclear overhauser effect, even tiny spectral features allow you to get information about assembly of protein in a complex units. And these all require much better energy resolution compared to that was demonstrated in the first experiment. Actually, after this first measurement of chemical composition, your Quackshuk group did experiments in very high field with NV center in 3 Tesla, and they have been able to measure chemical shift of a fluor-containing liquid above NV center, again with a sensing volume of about 100 nanometers across. So the chemical shift resolution was demonstrated. And to measure chemical shift, it's better to go to high fields because the shift is proportional to external magnetic field. For tinier features, like resolving J coupling, the spectral resolution is still a challenge. And so basically combining this single molecule NMR spectroscopy with high spectral resolution and high sensitivity to measure dynamics of molecule, this is one of the challenges in the field nowadays. I give you the state of the art, and if you like to learn more about this, you can look on this recent review paper. This is a benchmark of NV magnetometers in terms of application to detect nuclear spins. Here we show the sensitivity in terms of detectable number of electrons and number of protons within like 1 second measurement time or per square root of hertz. And on y-axis I show the sensing volume, or in other terms, sensor to sample separation. And what you see is that if you get very close, like in this experiment with single molecule, you can get to a situation where you detect a tiny fraction of the electron spin per second measurement time, and even to a single nuclear spin. So it's possible to detect one nuclear spin for 1 second measurement time in the very best case. But the spectral resolution, which is now shown in color, usually is not very high in this case. It's so far just to detect its hydrogen or carbon, but not about detecting chemical shift on J coupling. On the other hand, experiments with ensembles of NV centers are doing much better. So they are basically able to measure already now J coupling, in some experiments. In some cases, can follow even chemical reaction or transformation of molecules from the high resolution nuclear magnetic resonance spectra. Regarding the sensitivity, the sensitivity of NV center and ability to measure faster means you need higher sensitivity. That's as something which is defined by coherence time, as we have discussed. And when you are doing external molecule sensing, you're always very close to the surface. And surface is very complex object in all these experiments. So usually we just don't have external molecule and NV center that we sense. We also have an interface of diamond that might have some surface spins that we don't really control, and these spins are creating a noise. Some time ago, together with Neil Borgil, we have measured this noise using NV center as antenna. So here you see the noise spectrum. It's basically coupling to NV as an amplitude measure on y-axis and a frequency on x-axis. You see the noise peaks at low frequency, but also have a pretty high frequency components. And what you measure in the end, so here in the zoom, this is a hydrogen Larmor precession frequency. It's really on a high noise spectrum. All the experiments you have seen before were kind of trying to distillate the signal here shown in the zoom, on the background of the noise. Measuring better, measuring faster, measuring with less noise require better controlling surfaces or better controlling NV center spins, allowing to cancel effect of the noise. And so this is very important development.
What's the difference between the NV2, NV3, NV20, or is it
just different NVs? So we measure it about 50, and every NV has a bit different spectrum, and some of them are sitting in an environment with less parasitic spins, and some in an environment with more parasitic spins. Actually, single NV experiment is very forgiving because it's allow you to disregard NV2 and NV3 and just take NV20, which would have less noise, and then you can work with it quite a lot. If you do ensemble of measurements, sometimes it's more difficult because although you have higher signal, but you have to average our kind of all the population of NV center. In a single NV center, you are capable usually to select the very best NV in this regard. Yes. Yeah, it's also related to depth. Yeah, that's why also this lower noise for NV20. Yeah. All right. So how we can control this noise? Surfaces can be modified, although the nature of these parasitic spins is not fully understood, but usually etching of diamond a little bit and taking a very first layer away, terminating diamond with oxygen was shown to be very effective. Here I show you the effect of protocol, where you start with conventional acid boiling, where you boil the diamond in very aggressive acid mixtures, and then you do the edge of the diamond surface with plasma, and then you do annealing in the oxygen atmosphere. This leads to oxygen termination of the surface, and compared to just acid boiling, it basically lead to improvement for the same depths of T2 time of NV center by about up to an order of magnitude. Here you see the different NV centers as represented as spots. And so the yellow dots is traditional triacid boiling kind of procedure. And if you do this oxygen termination, you can get a longer coherence time for the same NV depth. So terminating surface with oxygen usually helps, but it's a bit empiric here, so there is no very detailed understanding of nature of the spin. Some of them are dangling bonds, possibly, but not all of them are fully kind of characterized. And so the other way, beyond the hardware kind of chemistry route to cancel the noise, is the quantum control toolkit, quantum kind of software path to this. And we typically control the noise by applying these pi pulses. I mentioned it before that making a spectrum analyzer out of NV center by applying many pi pulses already allow you to cancel many frequencies in the noise. In fact, you are sensitive in this case only to one frequency matching the separation between pi pulses, but all the others cancel it in this case. Conventional approach in this dynamical decoupling is to apply a train of pi pulses. The denser are the pulses, the better you cancel the noise. You will be sensitive only to one particular frequencies, but there are some limitations in the end. So if you want to cancel very high frequencies, you need to place your pulses so dense that they will start to overlap. And so there's some limitation in this respect. So the pulse technique are very standard, but they do have some limits when it comes to very, very short separation between pulses. There is another way to dynamically decouple system is just to apply a single driving frequency without any pulses. So if you take your two-level system, a spin, and you apply a drive with Rabi frequency omega, you create rest state. And this rest state, now having a state minus and plus as an eigenstate, are separated or kind of isolated from environment. If you want to flip this rest state, you need some energy for this. So you need some high enough frequency of the noise. This drive protect the rest state qubit against noise at low enough frequency. And this technique is very simple. You don't need any pulses. You just apply a single microwave pulse. Yes. There's a microphone.
You just said that by this continuous driving, it will go to this rest state, and this rest state is somehow for that moment kind of decoupled with the environment.
Decoupled from the noise, except the frequency that matches the transition between rest states. So
okay,
you can still sense, but then now you sense with a new qubit, and this qubit has now states minus and plus as eigenstate. And if your external signal matches this separation, then you will be able to sense. Yeah.
But answer the first question of mine, and the second is how it makes how these rest states are decoupled with this environment.
So they are robust against the environment because if you want to now perturb them, so you need high enough energy. So they will basically be not affected by any frequencies below the frequency of this transition between rest states. So there's an energy penalty. If you want to make a transition between minus and plus, you need to have at least this frequency present in your noise. Yes. So this is a way how to protect your system by drive. There is also some challenges here. So if your drive itself is noisy, you have microwave source, but it has some fluctuation in amplitude. That leads now to fluctuations in driving frequency, and now your energy level of qubit are fluctuating, and that's the same as decoherence. So the noise in the amplitude of the driving field will lead to kind of to dephasing of this rest state qubit. And the same is for the detuning. Also, if you have a detuning between your driving frequency and qubit, which is fluctuating, it leads to fluctuation of generalized driving frequency, and your qubit is getting a bit unsharp, so it's like dephasing for you. And so amplitude noise and detuning noise are typically a problem here.
One last question from this part is like, suppose there is like we are using a like perfect microwave source, and for that case, is that decoupling time scale limits by our T1 for that for our specific system, or like we can
One will limit, yeah. So the T1 decay is related to very high frequency processes going even to phonons. So you won't be able to decouple against T1 here. But I will show you one case where you can potentially decouple against T1, but not with this technique. Yeah.
Thank you.
So this technique works for low frequency noise as well as these pi pulses, but it can be very simple, but it suffer in this continuous way from the amplitude noise. But there is a trick if you do a second order drive, and even though your two driving fields, now you drive with two different driving frequencies, not only one, but you you have a second order drive that drives the rest qubit. Typically the second order drive is weaker than the first order drive. But if you have a right detuning of the second order drive, and these both drives are fluctuating, but fluctuating synchronously, and this is exactly what happens typically in your experiments, where you use the same microwave amplifier or the same microwave source. If you have your fluctuations present, they are usually correlated. In this case, you can construct the detuning of the second order drive, which will cancel the effect of noise of first order drive. And moreover, in this situation, there's a negative interference of noise that the noise in both fields is completely cancelled. So if you are just in resonance, then you will protect against first order drive noise, but they will still suffer from the second order drive noise. But if your detuning is just enough, or just precisely tune it to cancel the first order drive noise, but you also can have a constellation in the other direction, and the system can be completely cancelled from the noise if the right detuning is present. So you have two drives here, and they both kind of cancel noise of each other. Yes.
Right.
The bar qubit. This is, let's say, for NV center, ms equals 0, and this will be ms1. And this will be now coherent superposition and minus and 1 in a continuous drive. Yeah. And this is now fully protected second order drive qubit. And here I show you example how this technique works. If you use a first order drive, this is now oscillation of NV center. The oscillations are coming from this drive, but they are usually decaying, not because of decoherence, but because of the noise in the drive. And if you do this double drive picture, you can prolong your T2. You see the oscillations are persisting all the way to 3 milliseconds. And this is indeed limited by T1 time now of the NV center electron spin. You can prolong your T2 time all the way to T1 time of the NV center electron spin.
So when we say correlated noise, so does that mean the source of microwave drive is the same? Okay.
But it's also typical in experiments. So you usually don't do different sources for every drive. So you use, at least in many experiments, you use arbitrary waveform generator that generate many frequencies, and typically the noise is then correlated. The same device that create both drives. If this is not the case, then the scheme won't work so well. So it completely cancels the noise only if there is a full correlation in the amplitude fluctuations. So we can extend now coherence time of NV all the way to T1, and that, by the way, would correspond to about 10 nanotesla per square root of hertz of sensitivity in this regime per single NV center. We can also make this technique robust not only by the second order drive, but by changing phases in the drive. So you have a single drive, but you change the phase of the drive, and that leads to very similar situation where the noise is not relevant anymore, unless it's so fast fluctuating the drive that it's within one period here of this phase cycling. And also in this case, you can reach a very long coherence time, but now only with a single drive. You can also make this technique to be phase sensitive and now detect external AC field with a frequency resolution which is much better than the limit imposed by coherence time of NV centers. Here you see the signal of external AC field measured by a single NV center, and external AC field was very monochromatic. And you see that the line width of NV center measured by NV center is about 10 millihertz. So it's much better than hertz, even though the coherence time of NV is limited, but you can make the system to be phase sensitive against and beat it against a classical clock in the lab. And in this case, you can do spectral resolution much better than the one imposed by coherence time of NV, provided that the signal itself has enough coherence time. So we take it that coherence time is very essential for sensitivity. This is always true, but for spectral resolution, you can do better performance than 1 over T2 of NV if you make your measurement scheme to be phase sensitive. Okay. And since we had a discussion, so I just go on for another last few minutes and to finish this chapter. So I don't think we need a separate discussion. I think it's great that we discussed during the presentation. And here I would like to discuss with you a way how you potentially can improve T2 time of NV beyond the limit imposed by T1, and how you can handle very high frequency noise. Many things that are impossible with dynamical decoupling can be done with algorithm coming from quantum computing, quantum error correction. The question is how we can do quantum error correction for quantum sensing. So is quantum error correction useful for improving quantum sensors? So quantum error correction was designed for quantum computer to protect against external noise, and in principle against any noise. And it relies on redundancy in a system. Instead of having a single qubit, I now encode a qubit in a logical qubit. In the simplest picture, instead of having one system with spin up and spin down, I have now 3 qubits. And if one of them flips, I can now detect the symmetry of the system. I can ask now myself in measurements whether all the spins are in the same state or that one of them is opposite to another. And then without measuring really the qubit, just measuring the symmetry of the state, I can now say whether error happens or not. And after this, I can correct the errors. So the tricky thing here, I can correct the qubit, the logical qubit, even without sharp measurement of every individual spins, if this is 3 spins. Right, so because any sharp measurements will dephase the qubit, but here, so in quantum error correction, by using this redundant logical qubit, I can correct it without really affecting the phase. This is how the quantum error correction works. This is, of course, example for like more classical error correction, 3 eigenstates, but you can extend it to a quantum state too. So you need redundancy, and with more qubits, you can create both flip and phase errors. As it is something useful for sensing. When in principle, the fully corrected qubit is not a good sensor. Remember, in our criteria for quantum sensors, we define it one of them, that the system is responsive for external perturbation, and fully corrected qubit is not responsive anymore. But if you have a noise, which is a flip noise, and the signal is a phase, then you can still do better than without error correction. And I give you one example here, so how the error correction can be helpful in sensing. So this is now, again, a several qubit system in diamond, very similar to that I was showing before in context of quantum non-demolition measurements. I have an NV center and carbon-13 nuclear spin here, and this carbon-13 nuclear spin has a very long phase memory time, but is not very sensitive to external fields. And in NV center, electron spin is sensitive to external fields, so it's a good sensor qubit, but it has a short coherence time. And so combining these 2 in 1 allow you to go to sensitivity beyond the sensitivity of the NV center electron spin by using this clock spin as a resource. In the Pitt-Schmidt lecture, you had an example where entanglement is used to make better clocks, also using different types of qubits. This is now another side of it. It's 2 qubits you have, but they are allowing you to make a better sensor. So I'll show you very quickly a protocol how we do this sensing enhanced by quantum error correction. So we have now a 2-qubit system, and this is now energy levels, similar to that we had before for this QND measurements, but now it's carbon-13 nuclear spin. There are only 2 levels. It's a qubit, so it's this nuclear spin up and nuclear spin down, and this manifold correspond to ms-1 state, and the lower manifold correspond to ms equals 0 state. And we start here our sensing scheme with already entangled state. This is ms equals 0 nuclear spin down plus ms-1 nuclear spin up. So we need some work to prepare this state. I don't go into details how to do this. Take it as a given that this state is created, and now we leave it to process. So this state has a component of electron spin coherence. It starts to acquire the phase during this precession. It's the same Ramsey fringes we discussed before. And this angle associated with Lama precession of electron spin of phi, the phase, is now relevant for B-field measurement. Now, if you have an error here, and during the error, electron spin get flipped, at this moment, it starts to acquire the wrong phase. This is now dephasing. At this moment, you don't improve your measurement, but you rather destroy your measurement by dephasing. So for normal measurement, this will be end here. So any further evolution of the system will lead to evolution in the other direction and will destroy the information about external magnetic field. But if you now apply error correction, and I show you how it works here, it's just 2 CNOT gate and 1 laser pulse. So the error correction, it's on the right side. Take this state with the error. Remember, the right state is here, 0 nuclear spin down plus E phi minus 1 electron spin state nuclear spin up. So this is now after the flip, and the CNOT gate will now flip the electron spin conditional on nuclear spin. So if the nuclear spin is up, it will flip the electron spin state. If nuclear spin is down, it will not flip the electron spin. This is a very basic element of quantum computing, CNOT gate. Conditional flip of one spin depending on the state of another. So this now applied to this state lead to -1 nuclear spin up plus phase factor -1 nuclear spin down, nuclear spin up. This is now a disentangled state. So nuclear electron spin is now in -1 and nuclear spin is still in the superposition state. After this, you reset with your laser your electron spin. So -1 go to 0. This is your optical pumping. And now another CNOT gate. Remember, so this you now flip your electron spin 4 nuclear spin up. So this goes now to -1. And this one remain in 0, nuclear spin down. And this is exactly the state that you left your system before error happens. Application of this 2 CNOT and a reset allow you to take away the error. The entropy is taken by the light during the optical pumping in the system and reset to very initial state. Now you can continue to measure. And that's cancel your flip noise and allow you to continue to measure the phase of the spin. So of course you need many gates and you need them with a high fidelity. But here I show you how this NV center evolves. In the presence of strong noise, strong classical noise, there is no signal anymore. This is a blue curve. And if you apply error correction, so you recover your Ramsey fringes, and so you can measure your external field now. So remember the sensitivity is the slope here of this Ramsey fringes. And if you apply this error correction twice, you can measure for longer. Your Ramsey fringes get denser. You get a higher slope here, higher sensitivity. You can also measure the sensitivity as a function of measurement time. And even in the presence of a very strong noise, you follow the slope that is like without external perturbation. I even don't show here the kind of unprotected qubit because it don't have any sensitivity at all. The error was so strong that you don't have any signal. But here applying several error correction steps allow you to make a better quantum.
I have a question. Yeah, I did not understand where exactly this happens. This sounded more like an error mitigation technique to me than the error correction technique. I don't know if there's a difference between the two, and is it happening after we perform the experiment or prior to that?
I not only detect the error, but I really correct, right? So I restore the state which was before the error happening. It's not a technique where I have like active feedback, but for error correction is the condition for error correction is that you're able to reset the qubit. It's not conditional. So here I don't really watch this electron spin in real time and try to apply depending on measurement result. But the step of error correction is here. It's a conditional, it's a reset of the electron spin qubit in the right moment. So the error correction, well, it's of course set of all the three elements, but the entropy is taken by the repolarization of the electron spin. What I after this step, I get a state which is exactly before the error happens. So I fully restore my register, and the entropy is taken by light here, during the optical pumping. And yes, I need to.
I'm just confused about, like, you said you're not really watching what is causing the error and then applying the sequences. But let's say if it's some different form of error, it's not a spin flip, it's something else. then still the sequence will work. Or
Magnetic noise can be decomposed to spin flip and spin in phase noise. And so in principle, you can also now run this the same protocol with some additional rotation, and you can correct the phase noise. That would be good for NV quantum processor, and there is an effort to make it for NV quantum computer. It is, however, not very useful for sensor, because if I would run this as a correction of spin flip and phase noise, and I run it in a continuous, then my qubit won't be sensitive anymore to any magnetic fields. So then you are out of this criteria of a qubit for sensors. Then you are business with quantum computer, but not with a sensor.
Like while we are doing those operations to correct or error, in that time only it also gets some phase delta phi.
Time you say that there is a phase here accumulated, or or if there is, so that's need to be sharp here. So this need to be very fast, because indeed, so during this time there is still, you know, kind of if you accumulate phase during your resets and so on, that will be your parasitic phase. So your resets and CNOT gates need to be fast enough to not imprint any parasitic phase here. That's right. Yeah. Oh, okay.
Okay, I get the theory, but how do you practically A, generate an entangled state in this case, and B, apply the CNOT gate?
So it's a set of pi pulses or pi half pulses and free evolution. The gate to generate this superposition is based on dipole coupling, actually on this difference in splitting between this levels. So you can you first need to cool nuclear spin and electron spin to one well-defined state, and then use a dipolar evolution. It's just a few. It's actually so this sequence is a pi half pulse followed by some free evolution time and a dipolar interaction.